Cool. So, yeah, today we're just talking about some basics of quantum mechanics. I'm trying to keep this at a very high level without too much math. We will go into some of the math, and we're also going to talk about a little bit of the interesting history of the experiment and how the most significant results in the history of quantum mechanics and indeed much of physics came down to smoking bad cigars or cheap cigars in a laboratory. So that's kind of interesting historical story. We'll kind of contextualize things in terms of the history at the early period of time, why they were considering quantum mechanics, what were sort of the historical factors that played into things, how quantum mechanics fundamentally differs from classical mechanics, and then we'll briefly talk through at the end what the experimental evidence was, like why we actually considered quantum mechanics in the first place, and then finally conclude with a brief statement of what is quantum mechanics, and we'll probably have to go more into detail on that at a later time, although we could talk through it some more at the end after I finish the slides that I've prepared. So the first thing is, so this experiment is a very seminal one. You've most likely heard of the double slit experiment. You may not have heard of the Stern Gerlach experiment. This really was the foundational experiment. There were other ones, but this one is a very good one to talk about because it really encapsulates a lot of the core principles of quantum mechanics in relation to properties of electromagnetism, and that makes for a very theoretically easy derivation, relatively speaking, as opposed to going straight to something like the double slit experiment, which already requires a lot more theory. So this is actually a really funny quote. So if you read this initial quote, so this is by Walter Gerlach, which was one of the primary experimenters that performed this experiment, and in the background are the actual results of the experiment. We'll talk about what this means in a moment, but the one thing I want to draw your attention to is that these disks this is a 1 millimeter scale, and essentially these diffraction patterns that were measured, or the deflection patterns that were measured, if you can see, are fractions of a millimeter. So this was a highly, highly precise experiment done in completed in 1922. It took them about a year to complete. But this is actually kind of funny. So it says this was a letter to Niels Bohr, and Gerlach basically said, attached is the experimental proof of directional quantization. We congratulate you on the confirmation of your theory. Well, that sounds great, but Niels Bohr didn't really want this theory to be true, so this is actually a massive troll. They're basically, this is a scientific way of throwing shade, which is really funny. So we're going to talk about in this seminar, where do we see quantum mechanics? One of the big things that I want to sort of dispel as a misconception that I sort of had, and I think a lot of people had, is that quantum mechanics is somehow this abstract discipline that either doesn't have a lot of applications or is sort of like mystical in a way, and that's nothing could be further from the truth. So we're going to talk first, where do we see it? Why was quantum mechanics developed? And then finally, what is quantum mechanics? Like at its core, what are the postulates and the consequences of quantum mechanics? This section will be a little lighter in the slides. So as sort of we go through things, depending on how much time we have, it may make sense to kind of dive into the textbook a little bit. And then we can maybe look at some additional articles to sort of contextualize that last piece. The math then starts to get a lot more heavy, and we need to start talking more about linear algebra. So we may not necessarily get there, but we'll see how far we get. So the first thing is, where do we see quantum mechanics? And the way that my professor put it is, tell me where you don't think you see it, and I will tell you that you actually see it there. Pretty much all modern electronics in some form rely on quantum mechanics, because quantum mechanics is simply the application of physics to the submicroscopic or submolecular scale. Anytime you have photons interacting with atoms, interacting with electrons, those all imply quantum interactions. But here are three very clear interactions that would not be possible without the theory of quantum mechanics. The first one is solar panels. Again, because in a photovoltaic cell, you basically are having interactions between photons and single atoms producing excitations which produce electric current. That is not possible to model or engineer without quantum mechanics. Same thing with magnetic resonance imaging. This used to be called nuclear magnetic resonance imaging, but nobody wanted to get in a machine that said nuclear in it, so they changed the name. But this is another application that simply would not work without the principles of quantum mechanics to actually precisely measure the magnetic resonance. And we're going to talk a lot in this seminar about the principles of the nuclear magnetic moment, and that sort of pertains directly to magnetic resonance imaging. And then the final one is lasers. So this is a kind of cool one that came from the Wikipedia page. This is a guidance laser for a telescope. I don't remember exactly where this is, but same principle applies as sort of a solar panel, but kind of in reverse, where we're using excitations to produce light. So in terms of like where we see it, quantum mechanics is this strange but very precise world of observations and interactions of particles below the molecular scales. That's anything affecting atoms, subatomic particles, neutrons, electrons, and then various other things at the submolecular scale. The various sort of particle zoo, photons, all of those pieces. So,
can I mention one more effect?
Yeah, absolutely.
Pretty much everybody's LCD screen works on polarizing light, and then a pair of polarizing filters and rotating polarizations. That is a fundamentally quantum mechanical effect.
Oh yeah, that's another good one. Nice. Yeah, thanks for that, Totoro. So what I'm going to basically assert here is that the fundamental distinction between the classical limit and the quantum limit when we talk about particles, this is a little bit hand-wavy and there's a little bit more to this, but essentially in classical mechanics, we can know something deterministically if we know the initial conditions and we can make some assumptions. Those outcomes are typically distributed continuously, and we'll talk about the distinction between discrete and continuous values and what that means in a moment. And quantum, that's completely different. So particles behave probabilistically, meaning that even if we know exactly what the initial conditions were, we cannot actually assess what the outcomes would be exactly. We can only predict a probability distribution of what the outcomes will be. And that gets to some really interesting results that we can maybe talk about later. And you maybe heard of things like the Heisenberg uncertainty principle, the Schrödinger equation, Schrödinger's cat, and all of those are sort of consequences of this sort of probabilistic nature of quantum. So real quick, it's important, I think, to contextualize what we're talking about when we talk about discrete versus continuous values. I contextualize this here in the physical context and also mathematically. Discrete is a description of how many. Continuous is a description of one particular quantity. And you can almost think about this in terms of, these two examples I think are very precise for illustrating this. On the right-hand side, we have an analog mercury thermometer. And I think it would make sense to everyone that this can essentially take any continuous value between 0 and 30 C in this case, because it's driven by the physical inches or other methods to measure the height of the mercury in the bar. That's essentially a continuous scale. It can take any value in that scale. When we talk about discrete, a classic example would be the... Whoa, someone's hot micing.
Sorry.
Okay, no worries. Yeah, so when we talk about discrete, the Geiger counter is a classic example where we have emission of radiation. And this is also kind of a consequence of quantum mechanics as well, because we essentially have discrete particles, whether it's gamma, alpha, beta, neutron radiation. But at the end of the day, a Geiger counter produces as a measurement of those ionizing radiation events that hit the counter. And it's physically counting per second or per microsecond or whatever the refresh rate is, the number of such events that have been observed. So those are two very important things. The next thing is that if we talk about what classical mechanics is, we talk about the state of a system. So the state can be a variety of different things. We're really going to talk about position as the state of a system in this. As you get more into quantum mechanics, you can describe state in a variety of different ways. But when we talk about classical mechanics, one example would be the parabolic trajectory of a particle, which is, again, pulled from Wikimedia Commons, which is shown here. And if we know the sort of initial conditions and we make certain assumptions, like there's either fixed or no air resistance, then we can actually predict precisely the entire continuous trajectory of the particle. The state of such a system will then be continuous and can be predicted deterministically up to initial conditions and assumptions on the basis of Newtonian mechanics. So the classic example, particles follow a parabolic trajectory, and we can talk about what that means in more detail, but that's essentially the main piece there. So the next piece we need to talk about is electromagnetism. So this is the simplex of the conjugate relationship between the diamagnetic toroidal field that's inherent to all matter, of course, as Ken Wheeler would say, or we could say that it's simply the unified interaction between electric and magnetic fields. The first part obviously was a joke, and that's really stated precisely by Lorentz's law, or the equation for Lorentz's force, which is a statement about point charges. We can then extrapolate upwards to statements about continuous charge distributions, but it's actually not necessary for the scope of what we're talking about today. Talking about a point charge is sufficient for everything that we need to do. So Lorentz's law basically decomposes what's called the Lorentz force. You can call it an interaction induced by the electromagnetic effect, which is essentially describing a point charge interacting with an electric field and a magnetic field. So as we sort of move, we have a charged particle, Q, point charge. We have then an electric field that is being sort of induced through the space that this particle will interact with. And then we will also have this term, which describes its interaction with the magnetic field. That is a cross product, which is a vector product. And then by the right-hand rule, you figure out the cross direction that the magnetic force asserts. Real quick, we can look at the right-hand rule. I probably should have included that. I'm not sure if everyone has seen that, and that one is actually pretty important. There's two different versions of the right-hand rule. There's one for curl, and then there's one for the actual field force. But essentially, what it states in this context is basically it tells you, as a function of the cross product, the direction of the force that's going to be produced and the magnitude of the force, because vectors are quantities with magnitude and direction. So Lorentz's law basically is a nice description of electromagnetism. We can go a lot further into electromagnetism, but we don't actually have to. There's a few things that we do need to know, though. So this idea of an electric field is a consequence of Coulomb's law, as well as the statement of the Lorentz force. That's what's creating the electric field. It's a function of the of point charges or a continuous charge distribution. But magnetism is a little bit more complicated. In terms of what it can principally be produced by, and I'm primarily going off of the excellent Feynman lectures for this. So we can produce magnetism by like an electric current. So that's sort of what amperes, if you have current through a loop, for example. The magnetic moment of particles, which we'll talk about, and changing electric fields. And so all of those sort of things can induce magnetism, which will then affect charges via the Lorentz force that we talked about. So the next thing we want to talk about is why. Why was quantum mechanics developed? Because this is another thing that I think is extremely important, and especially in the circles that we sort of find ourselves in online here, there is a big misconception that quantum mechanics is somehow abstract and we're just kind of making things up and it's illogical and it's not experimental. Literally nothing could be further from the truth. It is unintuitive. It is maybe not what we would want it to be, but is an extremely precise, experimentally validated, and experimentally driven way of describing the world at that particular scale. So we're really going to talk about this through the lens of the Stern Gerlach experiment, which we mentioned at the beginning. We sort of showed what the two results were. We're going to talk about that more in detail. The text that I'm using here is Quantum Mechanics, a Paradigm Approach. But essentially, this wasn't the only conclusive experimental evidence for quantum. It wasn't the first use of quantum mechanics in the purest sense, but it was the first really, at the point when this experiment happened, most doubt was pretty much shut down that the theory of quantum mechanics was the way that things worked on this scale. It's extremely historically significant for that reason, but it's also actually conceptually quite simple. And we really only have to discuss the things that we talked about before: point charges, magnetic moments of particles, the Lorentz force, and then we'll introduce an additional magnetic force called the splitting force in a moment. And this is a really good framework for understanding the why and how we sort of get there. So it's a good framework, for the fundamentals. This is the textbook I'm using for my course. So far, it's okay. I don't know that physics textbooks are generally all that great, but this one's pretty good. So the first thing is the Bohr model. So we have sort of a history that goes into this of different atomic models. For the sake of time, I'm not going to cover all of them. But the prelude is that the Bohr model was elegant, as you can see from these beautiful drawings. These are from Project Gutenberg. These are actually the original drawings from the time of his famous lecture on this topic, describing essentially, how he conceptualized the structure of the atom as a function of discrete orbitals that surround the nucleus. So the important things to understand is this already was sort of a quantized model. When we talk about quantum theory, that notion quanta, is getting into discrete quantity. So thinking again about that left side of the screen that we talked about with the sort of Geiger counter recording sort of discrete events, that's just the way things are either best modeled or just actually sort of work on this particular scale. But this is actually quite controversial, and so one of the things that was noted was that the orientations are discrete. So again, you can see that instead of being a continuous cloud, there were sort of discrete positions that these electrons could be in, and in that sense, it was the first quantum model. Now, the interesting thing is Otto Stern. This was way before the Stern Gerlach experiment, 9 years before, hated this, and basically he and another physicist said, if this nonsense of Bohr should in the end prove to be right, we will quit physics. There's a lot of dramatic statements in this presentation. And part of what I want to communicate with that, again, is that, again, when we deal with people in this circle online, there tends to be this misconception that, essentially the theories were sort of always the mainstream and they were kind of forced on us. But the opposite is really true. I mean, the physicists didn't want this theory to be true in many practical ways. So when we talk about the initial model, basically all we need to know here is this idea of sort of orbitals and the sort of nucleus and the electron. And the hydrogen atom, of course, provides a very simplified model, only having one proton and one electron. And we'll sort of use that as a model to move forward. But it's really important that we describe this idea of a magnetic moment. So if you remember before, we said that Lorentz describes basically a point charge that experiences a force due to an electric field and a magnetic field. Well, on the basis of that, right, a non-ionized atom, meaning all of the protons and electrons are in balance, is not going to experience a net positive charge or a net negative charge. In fact, it's going to be neutral. It can be ionized, which is a little bit more complicated. We don't need to talk about that right now. We're really going to just consider ourselves with certain, particularly silver atoms that have a net neutral charge. So, nonetheless, despite not having a charge, and this is something that's kind of difficult to conceptualize at first, but it starts to make more sense as we go through the model. Some forms of neutral atoms will actually induce a magnetic field, and this is called a magnetic field associated with the actual atomic structure. And this actually applies to particles as well when we get down to the subatomic level, but for now we're just going to talk about it in terms of atoms. And this is really a function of what's called the magnetic moment. And so we're going to quickly derive and talk about the magnetic moment. And in physics, right, we have models. They are not necessarily a perfect representation of the world, but they allow us to apply existing principles to calculate quantities, which we can then use to build sort of predictions, test experiments, and things of that nature. So when we talk about the induction of a magnetic moment in a particle or an atom, we will use this idea of a moving charge moving around a ring. And at a more fundamental level, the higher level model is a current ring. So what we essentially have here is we have a ring with a certain area. It's going to be producing a magnetic moment perpendicular to, and again, this is going to be an application of the right-hand rule. So if you look on the screen, you point your finger up in the direction of the vector m, which is, in this case, is actually going to be mu. There's two different notations here, sorry for that. But that's the magnetic moment. And that directionality is determined by the right-hand rule. Your fingers are going to curl in the direction of the current ring, and your thumb is going to point essentially up in this direction. So that's basically a method for deriving the magnetic moment. So we're going to have, the current times the area. And to derive that, we're going to then work through this idea of a single charge. So we will have We will model this further as a point charge that circulates around the center. That's where this Q comes in, which you'll notice is the same sort of Q that we have in our Lorentz force. And then you might be thinking, okay, wait, but we were talking about a neutral atom. Why does it make sense to talk about a Q? That gets a bit more complicated, but basically the reason would be that this is only going to get induced when the structure of the particle or the atom permits us to talk about a particular charge that would be moving. In the context of an atom, like a silver atom, it turns out that there is basically one electron in the last orbital that will be sort of moving in a discrete path if we're using the Bohr model, which again, we know that it's wrong, but it is a useful model to start with before we get into more complex constructs. And basically what that's going to tell us now is that we can now derive the current, which is what we've done here. That's I. And then that's going to be a function of Q and V. V is actually the tangential velocity of the particle. And then we, of course, have pi r squared. So there's going to be a radius here of the circle, right? And tangential velocity is going to be a function of that radius. We do some math here. It shakes out to QRV. And then that turns out to be essentially, we can do some additional math, kind of hand wavy a bit here. But essentially that allows us to drive it in terms of angular momentum. And that's essentially how we do a derivation of the magnetic moment. And for the silver atom, which is what we're going to be considering for the Stern Gerlach experiment, because of the sort of orbital structure and the fact that we have that outer electron, we do induce a magnetic moment. That's not the only thing that induces a magnetic moment. That is a simplification. But for now, let's just think about it that way because it's a little bit easier than going through all the detail. What that basically means is that, well, atoms are magnets. Kind of, sort of, right? They're not exactly. But we can think about an atom with a magnetic moment as being a bar magnet with a north and south pole, and then we're going to have the magnetic field. The magnetic field being induced by the magnetic moment, which is modeled as the movement of charge. And this goes back again to our statement about the three different ways, fundamental ways that we can induce a magnetic field, which is this idea of moving charge is very fundamental to magnetism. So this is going to be important later because we're going to talk about how the model of a atom as a magnet relates to the Stern Gerlach experiment, where they essentially shoot these atoms through a magnetic field. But the first thing we want to talk about is another weird result that came around at this time, is something called the Zeeman effect. And here is another really dramatic quote from another physicist at the time, just to hammer home that they were not happy about all this stuff. They were not having this like orthodoxy that they really wanted this to be true and they were forcing through quantum mechanics or anything of that nature. It was very much we hate this. We would rather it to be a different way, but this is the way that it is. So Wolfgang Pauli, who's another famous physicist at the same time, was quoted as saying, and this is a longer quote where he's just describing himself being dejected on the street and having someone come up to him and ask him what's wrong. And he says, "How can one look happy when thinking of the anomalous Zeeman effect?" I guess that's a physicist problem, but the Zeeman effect is a little bit harder to describe because we need to talk a little bit about spectrometry and interference patterns. But basically all you need to know is there was this anomalous pattern that was detected that could not be really explained well with the existing models, which is kind of what Pauli is talking about here, where if you apply a magnetic field to in this case it's a mercury vapor lamp, you get different spectral lines when you do spectroscopy. And you'll see that the spectral lines vary as a function of the magnetic field. And basically all that means is that we see an anomalous effect in the way that light propagates from mercury vapor, which could not be explained classically. And so this is kind of how we knew that at the time that, again, Bohr model was elegant, and it was kind of wrong in two senses. It was wrong in the sense that people didn't want it to be true, that it was sort of this quantized thing. But it was also wrong in the sense that it wasn't able to really predict the Zeeman effect, and it also didn't really predict accurately the magnetic moments, although that wasn't known at the time. So the next thing that we need to talk about to really talk about the experiment of Stern and Gerlach is this idea of the splitting force. So notice that we talked about the Lorentz force as the primary sort of motive force of electromagnetism, QE, again, plus V cross B. But again, we said that the silver atoms are non-ionized, they're neutral. So Q is 0, therefore this force is 0. And what that means is, if we put the silver atoms, next to sort of this field, we're not going to be inducing that net charge and experiencing that Lorentz force. But what we do experience is what's called the splitting force. This is kind of how it's been described to me, but there's not really a great name for what this is. But the idea here is that if we have an atom with a magnetic moment mu, and again, we talked about, the effect. Oh, someone else is hot micing. But yeah, basically, we'll define the splitting force. The splitting force is really a function of a gradient. So let me try to find this because I don't actually have a good diagram in the presentation. So this is really only relevant to an inhomogeneous magnetic field, which, again, that gets a bit more technical. But what that basically means is that it's not uniform. So here you go. This is this is actually exactly what we're talking about. So, and this is probably related. Yeah, here we go, Stern Gerlach, exactly. So if we have a non-uniform field, it means that the field is stronger on one side than it is on the other. And the side that it's stronger on, this might be counterintuitive, it's actually the top side here, because we have a higher density of field lines within a certain area, and that's going to contribute to a stronger magnetic field B. But basically what that means is that if we're moving something through here, like our little bar magnets, they are not experiencing a net force up or down due to the Lorentz force, but what they are experiencing is a force due to the gradient. And this splitting force acts in a very particular way. So it acts on basically the gradient. In this case, we're going to look and this is a good figure actually, this isn't just in the z direction. And in practice, we could have aligned this in any number of ways. This is just the best way that we could set up the experiment. But you're going to have essentially a splitting force in one primary axis. Technically, there's other terms, but they're really close to 0. So we just say it's approximately, we pull the mu out, if you remember your calculus, because the magnetic moment is going to be constant relative to the field. It's not changing based on the field, right? What is changing is the magnetic field. So then what we have is the splitting force is roughly, or we could say proportional to, mu z times the partial of the magnetic field with respect to z. And all that's really saying is there's going to be a force here which acts in a way that will essentially split the beam. If we have a flow of particles, they're going to get affected in a way that they're deflected. They go up and down. And we'll talk about what that means more in a moment here. Sorry, this slide is a little bit messy, but this is all pulled from this great article, which I would recommend you read, from Physics Today back in 2003, which talks about this. But basically, we knew that the Bohr model was kind of wrong, and Gerlach had some ideas around using particle beams to test it. And specifically around this idea of the splitting force that we knew about at the time. And Gerlach didn't really think this was going to work, but this is another quote that I think is really important for us that are sort of in either studying science or trying to educate people on science or debate science or anything like that. I love this quote. No experiment is so dumb that it should not be tried. And so Gerlach said this, but Otto Stern was really the one that came up with the realization of how this would be functionally tested. He realized that basically, while we looked at all of these different orbitals, in reality, there was only a fixed number of a subset of the states that were actually relevant. And basically that what they call here the twofold character means that he was thinking basically that there should be two states that it gets split into. In the classical context, though, remember we said that that's not what we think about, right? We think about a trajectory, we can predict the trajectory, and we get a continuous distribution. So this is already very different thinking. But this is what I'm saying about like sort of the quantum mechanics and the nature of experiment, right? This was very much a process. So the other thing we need to talk about a little bit is this idea of precession. Basically, all that means is that in classical mechanics, the splitting force, so as these atoms move through, they're going to precess like a gyroscope. And that precession due to the splitting force is going to cause them to split into a continuous, it's going to basically make the beam wider. The beam of atoms as they go through, it's going to be wider. That would be the classical prediction. The difference is the quantum prediction would be that there would only be two states. And so this is the classical expectation. I pulled this, again, here's the link here. I'll provide these slides as well. But according to the classical theory, a particle beam of silver atoms passing through this inhomogeneous magnetic field will experience a splitting force, which will result in this, it sort of looks Gaussian. It's not actually Gaussian, it's sinusoidal, but just, it squint and look, it kind of looks like a Gaussian. It's kind of uniform, right? And that kind of makes sense classically, right? Because if we knew where we're starting from and we're sending it through, then we should be able to predict in some sense where the particles are going to go. They're going to get split in a certain way based on their initial orientation in the field. So to test this, they defined what's called the Stern, I should dash this, one second, the Stern Gerlach apparatus. The Stern Gerlach apparatus, again, so we had a, this is kind of really old school technology. Again, this was 1921 when they started this. It took them about a year to finish it. This is by this user, Tatuit from Wikimedia Commons. Thanks for putting this together. And this shows a lot of cool stuff. So the first one is that we have a furnace that produces the beam. We have a collimator, which focuses the beam. And then you can see this inhomogeneous field where the top is in the Z direction is stronger than the field in the bottom Z direction. And essentially what that tells us is that, again, we're going to have a splitting force because there's an inhomogeneous field. Now, what's really cool about this, and this is a little bit approximated, is that this is the expectation classically versus what would be observed if Stern's suspicion was true. But this was the problem. They were getting very difficult results. They did this for over a year, and this is where a very interesting historical story comes in, because what happened was they had these screens, and they had all this in a vacuum, of course, but silver atoms on the screen, they weren't able to get a very tight beam. I mean, again, we're talking about, this is back in 1921, right? Being able to get a particle beam in 1921 is pretty freaking incredible when you think about it. But collecting the particles was different. So all they had was a thin layer that wasn't really visible to the naked eye. Again, all this is in this great paper, which I recommend you read. It's a little technical, but it's really great. And so what was really interesting, though, is this was old school, right? This was back in the day when you wore a suit in the lab and smoked cigars. Well, at the time, so what this quote says is, I'll just read it out in full, but with Gerlach looking, so this is from Stern, with Gerlach looking over my shoulder as I peered closely at the plate, we were surprised to see gradually emerge the trace of the beam. Finally realized what had happened. I was the equivalent of assistant professor. My salary was too low to afford good cigars, so I smoked bad cigars. These had a lot of sulfur in them, so my breath on the plate turned the silver into silver sulfide, which is black, so easily visible. It was like developing a photographic film. And what did we observe? When the beam went through without the magnet, it would produce this solid beam. And again, we're talking about a sub-millimeter scale. Like, this is mind-blowing how precise this was. When we applied the inhomogeneous magnetic field, what do we see? We don't see an even smear with, again, going back to the classical prediction, we would expect everything to be evenly distributed. Instead, what do we see? We see two states. And that is the confirmation that quantum theory was correct. So what is quantum mechanics in this context? So this section's a little bit lighter than I'd sort of hoped for this presentation. We can maybe have some more discussion at the end here. But, as we said before, the result that we expected classically was not what we observed. We did not see a continuous smear of atoms that was just predicted by precession. What did we see? We saw these two-state splitting. That is quantum. quanta. To understand why this will occur, we're going to define something that's a little bit of a tricky name. And again, when we talk about physics, we like models for things. We like them to be as precise and accurate to the reality as possible. This is one case where we're a little bit pushing it, because we have this idea of spin, which is also called intrinsic angular momentum. And this goes back to this idea of modeling the magnetic moment of the atom as a rotating charge or a current ring. And if you think about it, there's going to be an angular momentum, right? This is this quantity L, and we have this quantity mu, which is the magnetic moment. So that's sort of related to momentum of the particle, and that's angular momentum computed using the tangential velocity. And so what do? We define something called spin, or intrinsic angular momentum. So I had to kind of go and find this because the book didn't really explain it that well. But essentially, you have now this other article that I can point you to. But basically, what spin is they define it as an essential property that influences the ordering of electrons and nuclei, which is set to affect the physical properties of the particle, and in particular, the magnetic moment. So they do a derivation in the book. I'm not going to torture you with it because it's fairly involved. But we introduced this G factor, and this is actually experimentally measured. This is called the gyroscopic ratio, which is a measure of like the conversion to angular velocity, or like intrinsic spin. It's a way to relate these two. And then we essentially have the mass and the charge, and then we have the spin. So the key idea here, though, is that, again, we looked at what we expected, we turned the field on, and we didn't see the classical result. We didn't see something that was a homogeneous or what looked to be homogeneous distribution. What we saw instead was two states, an up state and a down state. And it turns out that this explains precisely the distribution of the particles observed in this experiment. So this is one of the key principles now of quantum mechanics. Spin, which is this fundamental property of particles, is quantized, right? It is fundamentally existing in discrete states. There's no continuous distribution between them. And it turns out that we can precisely build the distribution of the particles using quantum theory to exactly predict this distribution here, which is what I have to do for my homework. The next thing, though, which is a bit harder to understand, is that the predictions become intrinsically probabilistic. So when we talked about the parabolic trajectories in classical Newtonian mechanics, if we knew where the particle started and we knew certain aspects of it, we were able then to derive precisely where it would actually fall. In quantum mechanics, that's not actually true anymore. And again, to think about why, we have to think about the fact that the spin is quantized between the two states, and as we move through the field, this inhomogeneous magnetic field, it has an equal probability of attaining either state. And functionally what that means is when you send it through, there's a 50-50 chance it's going to go up or down. And therefore, we can very precisely describe which of the two states it goes into, and we can actually just derive that distribution, which I said is sinusoidal. But what's going to end up happening is we get a probability distribution of the particles. We don't actually get deterministic predictions. And so when we say what is quantum mechanics, there's more detail to it. We can talk about this a bit more. But the key thing is quantized. Everything is quantized. The classical theory of a continuous state that we would expect, again going back to this slide, is not what we observe. Therefore, the classical theory was wrong, right? It didn't agree with experiment, as Feynman would say. Therefore, the quantum theory was found to be correct, and this experiment was repeated, and multiple doom experiments were done. And so, spin or intrinsic properties of particles are quantized, and predictions are probabilistic. And that's where we get back to the beginning with this, way for Gerlach to throw shade while sounding really nice. You had this theory, you didn't want to be true. Congratulations, it was actually true. So that's mostly what I have. I can kind of stop for discussion now. I did gloss over a few things, so if you have any other questions on specific points, we can dive into that. We could also dive more into the math, talk about like the how we actually derive the probability distributions. But yeah, I'll just kind of open the floor for discussion if anyone has any questions.
I got a stupid question.
Yeah, go for it.
How do you know how the atoms interact?
With what portion? With the magnetic field or with the screen?
In general, how is it known how atoms behave? Sorry.
No, that's a great question, actually. That's a very good question. So this is again where we have models and experiments, right? And I don't 100% know the history of the derivation of the Bohr model. We could look into that more. There was the, different models prior to that were more sort of atomist, where we had everything sort of clumped together. And it was a really revolutionary idea to begin with, and it was based on, so there was the Rutherford gold film experiment. I don't know if you've heard of that one. And these are all sort of classical experiments prior to quantum. But let me kind of talk you through this briefly. So this was one of the ones that actually was able to determine, confirm sort of some of these early ideas, to get to your point, like how atoms actually interact. But the other piece is that we know that we have a certain model, right? And we have a way of representing the properties of that model. So we have Coulomb's law. Let me see, because I have some stuff in my notes here. Let's see, we got a bunch of stuff in here. Lorentz force. Right, so we have the Lorentz force. Massive neutron, that's different. Lorentz transformation, Stern Gerlach. Theory of ballistic, yeah, that's all different. But I think, so fundamentally, there were certain models and experiments that were done prior to this that determined properties of the atom and sort of interactions and bonding and things of that nature. But this experiment primarily concerns the interaction of the magnetic moment, which defines basically a model of the atom as sort of like a bar magnet. Again, kind of, sort of. Like when we're talking about physics, it's not like it's actually a bar magnet, right? And it turned out there was a lot more to the structure of the atom than the particles that were known at this time. But we knew that roughly we could derive this magnetic moment using this sort of model, and that would describe how it interacts with a magnetic field. Because the net charge would be 0, and this gets into, I have a bit more detail on the silver piece. Where is this one? Okay, so bear with me here a bit. But so a silver atom has 47 electrons, 47 protons, and a certain number of neutrons. We actually have this was originally measured experimentally, that these sort of ratios held. Because the electrons and protons are in balance, there's no net charge. Therefore, we don't have a Lorentz force. It's not an ion. But the magnetic moments are somehow related to the inverse of the particle mass. Then we get into chemistry and orbitals, but you notice at the end, so we have 1s2, 2s2, 2p6, 3s2, but at the end we have 5s1. So in the 5s orbital, and this is going off of the Bohr model, there's one electron sort of kicking out by itself there. What that basically means is that the interior electrons are sort of balanced in a way, in charge, in sort of an equal and opposite way, and therefore they don't contribute to the magnetic moment as much. What's actually contributing to the magnetic moment is the last electron that's kind of spinning in the outside orbital. And that's how we can derive basically the magnetic moment as a function of that electron, and then derive the splitting force. So this is a little bit more detail. And that's the splitting force, which we can, again, experimentally measure, will then tell us how it's going to interact with the magnetic field. And then once we set up our apparatus, we know that we're producing a stream of these silver atoms. Again, we can sort of observe the properties of the silver when it lands on the end of the apparatus. and we know how it's going to interact with the field because of that intrinsic magnetic moment. Does that kind of answer your question? Because it was actually a really good question. I'm not sure who asked that, but
Yeah, kinda. So I don't know if I understand all of it, but is it that there is a consequence? There's a consequence every time this stuff is tested, or is it more than just consequence?
so every time we repeat this experiment, we would get the same result. There's a postulate as to why that would occur, which is based on all the principles that we talked about. Things like magnetic moment, charge, the neutral particle still having a magnetic moment, and the interaction with the magnetic field. So we have basically experiments that lead up to this one that build up our experimental knowledge in the laboratory of all of these different effects. And then we develop these mathematical models to describe those interactions. And then from that, we basically are able to induce from the experiment the effect that we're observing and the reason for that effect. But at the end of the day, like I said, like when we talk about spin and like angular momentum and these sorts of things, it's not like we're actually going in, especially at this point in time, we're not like actually going in and measuring a angular speed and things of that nature. A lot of these constructs are theoretical to describe things that we can't directly observe per se, but they give us a useful construct that we then test if it has predictive validity. And what we observe experimentally needs to confirm the result.
Cool. Thanks. Yeah, that answered it.
Cool. Yeah, and then we could talk briefly. So I don't know how much you guys want to get into this now, but I could go to the end of the hour at least. This is starting to get a lot more complicated, but another thing that they did to extend this experiment is you can actually now take differing levels, and this is where we get into more detail on the probabilistic nature. So basically, we have this idea of the quantization. We said we could derive the splitting force. We can derive that in terms of the spin, right? The magnetic moment, the spin. Those are kind of intricately related concepts. This thing that we call intrinsic angular momentum. We can then break down the component into like the cosine of the angle between the z-axis and the direction of the spin. And then this gets a lot more complicated, but basically at the end of the day, what we get is two states, which is what we have here, plus or minus what's called h bar over 2. And this is kind of one of the key things of quantum, right, is that it's a quantized state. And this is the thing that I had said that, and this is where sort of like genius, or what I like to almost call like the muse comes in, right? He essentially, I don't want to say guessed, but he had a postulate or a hypothesis that this would be the case. So he had analyzed, he looked at this model, which initially, again, we didn't even want this to be true per se. And he realized that it was sort of a more complicated, like there was a subspace of the orbitals that was really producing most of the effect in this particular example. And so what he looked at was that, again, the quantization would only be in those two directions, which are a function of the bar didn't copy over, but h bar over 2, plus or minus. And then this is Planck's constant, which is just a measurement constant. We have a lot of different constants that we can measure in science. And we talked about the quantization, but then basically we can do additional stuff. So this was the initial Stern Gerlach. And now we can get into a little bit of the math. I don't want to get too deep into the details, but we have what's called Bra-Ket notation, which we use in quantum mechanics. So we describe the state with what's called a ket. And so what you can see here is that if the beam goes down, we have a negative ket. If the beam goes up, we have a positive ket. And this is an encapsulation of the state of the particle, which is again a function of the intrinsic spin. And this is this is interesting because when we first walked into the quantum mechanics class, the first thing he asked us is, can you derive Newton's second law? And the answer is actually technically no, because unless you are kind of going off of the other laws potentially. But when we look at all of Newton's laws, they weren't derived as such. They were postulated. He had an idea, he tested it extensively with experiments, and then that's how we sort of derived those physical laws. So in a similar way, we postulate a statement based on a ket, which is basically that the state of the entire quantum mechanical system is represented by a ket, and then we normalize it, which essentially just allows us to compute probabilities off of it. And basically what we see, so there's some other interesting things that happen, right? So if we have a splitter early on, and we split all of the negative kets, and then we send all the positive kets through the next layer of splitter, they don't reorient themselves. Because they've been selected based on spin, the ones that go through again are only ever in the up state, never in the down state. And this also plays into our understanding of why quantum mechanics has to be probabilistic, is we see sort of these sort of relationships. And we can talk about a bit more, look at the other postulates. These are more complex experiments. It gets increasingly complex. Double slit experiment, I'm not going to talk about that. Then we talk about quantum state vectors and Hilbert spaces. Hilbert space is just a convenient way to represent kets and quantum states and represent probabilities. Let's get to the next postulate, though. I'm glossing over some of the details here, sorry, but the math gets fairly involved here. So postulate 4, which is relevant to the spin 1/2 system, and these are kind of out of order because other ones are going to be derived later on, is that we can derive the probability of obtaining a value in the up state or the down state, which is a perfect encapsulation of the state of this system. It can only go up and down relative to the beam that's sort of a fixed initial state. Basically is equal to the square of the amplitude of the normalized ket. And this is what actually creates a probability amplitude or a wave amplitude. And this is where we start to get into thinking about particles as waves, like why that construct is useful. That's basically all I have, unless anyone else has some other questions. But thanks otherwise for your time. This was really fun. And there is a simulation software that they reference here that I want to take a look at, because I think that would be kind of fun. Oh, and this is actually kind of cool. Let me show you this, because this is actually a really cool illustration of a case where what happens on the macro scale is pretty much identical to the micro scale. So if we look at matter waves on pond, let's go to videos here. Interference. There we go. Forward here.
What is light?
Okay, let's see if we can find where the actual experiment happens. So these are called de Broglie waves or matter waves.
This pattern is created by the ripples from the two sources interacting with each other. Where they meet up, peaks with peaks and troughs.
So you see this, you have an initial set of waves, and you have patterns of constructive, where the waves add up, and destructive interference. And it turns out that that pattern of de Broglie waves actually is precisely relevant to the case of the double slit experiment, which produces, a interference pattern with photons. But the same actually holds when we send particles. So if we send like neutrons or atoms through, we'll observe the same sort of de Broglie waves, which is a cool example of, physics on the macro scale modeling what we see on the micro scale. Yeah, that's really all I have. So any thoughts, feedback?
You mean de Broglie waves?
Yeah, am I saying it totally wrong? Sorry about that, Totoro.
No, it's just okay. It's just a or De Broglie sometimes. But
Yeah.
there's
De
no
Broglie,
D at the end.
isn't it? I thought it was De Broglie because I like his model of the photon. That's the model I subscribe to. De Broglie's model.
Yeah.
Yeah, you were saying De Broidel.
Yeah,
Or
sorry, I
something
just
like that.
totally butchered it. But yeah, any other corrections? Because I am pretty new to quantum, so if anyone else has any other thoughts or points of discussion. And thanks for joining, Cirrus. I know we talked about having you come by, so I appreciate you dropping by the server.
Dude, I fucking love it, man. Why don't you do this on Geos? Because I think if you walk flat earthers through this the way you did, I don't think you get that much resistance, man.
He would get massive resistance. Massive resistance. They're all.
Some, but like this is really breaking. I love it, man. It's great.
Well, I appreciate
10
that
out of
feedback,
10.
man. I'd be totally down for it. Yeah.
Dude, you should. Fuck yeah! I'll talk to Gio or something. Like talk to him about it because, like, I don't know. 2 thumbs up, man. It's good shit.
Appreciate that, man. Yeah.
You're a good teacher.
Thank you.
Have you gotten? How far are you in quantum?
The first week.
Dipoles and all the positron electron pairs.
No. I'm in the first week. I don't even know how far we'll get into it because this is only an introductory course as well. So I can show you the syllabus if you're curious.
Sure. Go for it. I bet.
The
minute you mentioned De Broglie, I was like, yes, De Broglie is my boy, man. His
Nice.
model of the photon is where it's at.
Is my screen still sharing? I think it is, right?
Yep.
Okay.
I believe so.
So this is all we're going to cover, Cirrus. So we're starting. So first week was just Stern Gerlach.
Did it just start Mordwand, bro? I just got here.
Yeah, I'm sorry.
Alright. Bro, good, bro. I'm in time, man. I'm happy.
But
There was a suggestion, or somebody was asking about it earlier in chat, whether this is going to be recorded and available later. So for the feature, I would recommend that you also OBS record this and possibly upload to YouTube for later.
okay. Yeah, I did do a screen record on Mac, but that OBS would be better.
Yeah, guys, type shit, bro. I'm trying to have this available.
Nice. So I don't even know what a lot of these things mean, Cirrus, but yeah.
Yeah, I'm reading it. Interesting.
Quantum spookiness. I know that has to do with interaction at a distance and entanglement, spin precession.
Entanglement, yeah.
So are you familiar with torque and like torque on the magnets and how that relates to precession and like gyroscopes? It's really interesting.
The quantum torque? Yes. Or which torque?
So when you send
At the quantum level?
yeah, like the atomic level. So when you send these so if we go back to the Stern Gerlach again, when you send this particle beam through the magnetic field, precession actually explains like the reason that the beam spreads out like this is due to the particles precessing in the magnetic field, and that will happen classically. But that precession explains it due to the splitting force. Splitting force is in some way like inducing a torque, because again, like we're saying that like atoms are like magnets, right? They're kind of like a bar magnet, kind of sort of.
What is precession?
Precession, that's harder for me to define, but you know, like how Totoro, could you maybe jump in on that? Because that's or Totoro's gone.
Just bust out Google gyroscopic precession. It's pretty simple.
Yeah, classically,
any spinning like particle. Yeah.
Classically, it is explained as precession being a property of an object that has angular momentum. The angular momentum is going to be aligned with the axis of rotation, and precession is the act of the axis of rotation itself, slowly rotating around sort of an invisible. You can think of it like a loop on either end.
Hey everyone, Derek.
Or just basically changing the axis of rotation.
From the rotating axis, you could call it R. So the torque
Alright, this thing.
is actually here.
Oh, yeah, I watched this video actually.
Yeah, so when you apply a torque on a gyroscopic system, its axis of rotation will slowly turn around.
Out towards the camera, out towards you. Now, before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum round that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel.
Cool. Yeah, so that's basically the same principle, right? The same principle applies. So basically, because they have an initial angular momentum going into the, that's how we model it, right? Because when we talk about angular momentum of like the intrinsic angular momentum or spin, that's that kind of idea. And we talked about like the charge kind of moving around the current loop, but they have an initial angular momentum in like a magnetic sense and electromagnetic sense. And as they move through the field, they precess, and that precession causes them to split along different trajectories based on their initial.
You're talking about the laser going through the magnet, right? The magnet, or like the magnetic fields, is what causes the precession, yeah?
Yeah.
Yeah, right, makes sense. Yeah.
Because if you
By the
think
way, your stream cut out.
Oh, okay, yeah, no, I stopped streaming, so. Seriously, I want to talk about the gravity thing, but I am fucking exhausted. I pulled an all-nighter last night, so I might have to rain check. But I really appreciate you stopping by, because I think you have some...
Dude, no worries, man.
Yeah.
We'll chat for sure, man, since you're studying quantum mechanics.
Yeah.
So am I still. It gets thick, but I like it.
Nice.
It's good shit. Yeah, man. I appreciate the presentation, bro.
Yeah, absolutely.
Thanks for inviting me.
Thanks, everyone, for coming. I mean, you know, I'm interested in doing more of this stuff, so... I have some cooler other topics. Like we did last week, we did computer vision and like how camera sees and some like optics, and like, you know, world, like figuring out where the camera is, like camera poses and stuff. Yeah, so yeah, sorry, I know we have a lot of people on the call, but I am freaking exhausted, so feel free to hang out and chill. And I think we have couple moderators kicking around, but I need to go grab some dinner and go to bed. I'm freaking exhausted. But thanks so much, everyone, for showing up. I really